Hi friends, welcome to the next session. In this session, let us see how to create our robotic system using the reinforcement pattern. One option is use a simulation to build a model or directly use the real world training. So there are two ways of doing it and we need to understand what the difference is. So in the simulation system, we will have a virtual environment instead of the real environment. We will have a virtual environment, and the state of the virtual environment is looked by the simulator, and then uh, the actor sees what the state of the environment is, and accordingly takes an action, and this action will provide a reward and making the state to change. So this is again visible on the virtual environment, and this process continues. So for a given situation, we create a virtual environment, and then the whole learning activity is done on the virtual environment. And once we feel that our agent has fully learned, then we can make a trial on the real world environment. Otherwise, we can directly start training in the real world. So the agent interacts with the real world environment and makes actions, and because of those actions it will get rewards or punishments, and this will help in creating a policy, and this policy will be used for future actions. So the advantages of using simulation, more only in terms of cost and safety. So it will be safe when it comes to experimentation. Instead of real-time experimentation, we can make it simulated, and it will be definitely safe. So, for example, if you are working on self-driving vehicles, then instead of experimenting on the real-time road, better work on the virtual environment and make it a simulation and see how the vehicle moves or different obstacles, different situations and all that, and then come out with a policy. So the cost will be less because all the training and all is done on the simulation, so doesn't make much of the expenditure, and most importantly, it is safe to work with. Second thing is when you are working with simulation, the training will be fast, training will be cheaper, and most important thing is it is fully observable. That means the whole environment is fully observable when it comes to simulation. But when it comes to real world training, experimentation is not safe. Training is very slow, and it's going to be highly expensive, and only partial observability is there. Then there we can build a reinforcement learning system using simulation. But when you want to really implement it, there will be gap, and these gaps can be filled using techniques like domain randomization, fine tuning, etc. So the problems in simulation, of course, simulation also doesn't work very well because during simulation we assume everything to be perfect, but in real time, definitely nothing will be perfect. So the policies that are trained in the simulation may not work very well in the real world for many reasons. So the reasons may be noise from the sensor. When we are simulating, usually we neglect the sensors noise and all that. So we assume that all the sensors are ideal. Therefore, the signals coming from the sensors are assumed to be ideal. And but when it comes to the real-time situation, no sensor is ideal. So every sensor signal is associated with some sort of noise. And if this noise is not considered while training during the simulation, then it's going to be a tough time when it is being implemented in reality. The other problem is about the actuator relays. So usually when you say actuators, they are either electrically operated or pneumatically operated or hydraulically operated depending on the power requirement. Now, if it is pneumatic or hydraulic operated, then definitely when we say close, the very same instant it will not be closed. It takes some time to move. So if you are saying to grip something, then the moment you say grip, it starts moving, and then it takes some time to have a proper grip. So there is delay from the instant we say grip and the instant where it actually grips. And these delays depend on the real-time situation, depend on the actual actuator. So it varies from actuator to actuator, and it is difficult to add up all these delays into the simulation system. But of course, if it is added, then things would be even better. But most of the time, we forget to consider these delays above that. The other physical problems we do face is about the friction, mass, dynamics, and all that, which usually we may neglect in framing the policies. And of course, many unmodeled real world variations are there, which we might not even have dreamt of during the simulation. But when it comes to the real time situation, a lot of problems we do face. So, one thing is either train the system under simulation and then convert to the real time, or directly train in the real time itself. So both have their own pros and cons. So the pro of simulation is safe experimentation, faster training, cheaper, fully observable. But working on the real world training, experimentation is not definitely safe. Training is very slow. It is going to be too expensive, and the environment is not fully observable, and hence the policy has to be decided only whatever is observable, and most of the things are uncertain. So everything has to be stochastically worked out. Along with that, we will have noise from the sensors, delays in the actuators, and all other situations. So if we want to avoid these problems, like the sensor noise, actuator delays, and all that, then we could go for real world training where the training is done using the sensors, real-time sensors, and these sensors will provide the signal along with the noise, so the system gets trained along with the noise, and the system will be trained along with the actuator delays and all that. So the delays are learned, noise is also learned. So there are differences in the friction, mass, dynamics, and all. If at all is there, it is considered during the learning stage itself, and we can see that most of these problems can be solved if we go for real world training. So now coming to the bridging this gap between simulation to the real world. So we can go for domain randomization, that is while training, there are many physical parameters used. So we can randomize these physical parameters during the training. So because of this randomization, the agent will learn a robust policy, and that will be helpful in generalizing when the real world variations come into picture. Or you start with a simulation on the ideal situation and then get to the real world and then start fine tuning it. So that's another option we have. So there are some challenges we have when it comes to real world challenging training. It is highly time consuming, lot of hardware limitations we do have. We have to worry about safety concerns, and the environment is partially observable. And if our training fails, so if whatever we are doing, and if it doesn't serve the purpose, then we need to reset our whole activity and restart again. And that is going to be a very expensive one because we have to really build a physical system. And then, if you feel that it is no more useful for the situation, then the whole thing goes waste. We have to build again everything from scratch, so it's going to be very expensive whenever you try to change the situation or when you try to reset your models and all that. But the situation in simulation is not so. It is just going to be changing the parameters and all that. It's all numerical modifications have to be done. And, and hence, changing the model or changing anything doesn't need any expensive actions, so it will be very quite cheaper when it comes to simulation. But problem is simulation, we have seen that when you are changing to real world, we do face a lot of problems. If you don't want to have that problem, then we should go for real world training. Yeah, they have their own challenges. So in this world, nothing comes freely. So one side, some things are positive, then other side, there will be definitely some negative aspects of that. So that's about the real world training and their challenges. So the various approaches we have. When it comes to real world training, it can be a batch processing or offline processing using the lots of real world data. So take the real world data and then dump it onto the machine and ask it to learn. Second one is human in loop reinforcement learning. So human will be useful in observing what the machine is working and anywhere the machine is erring, then human can give appropriate feedback and make the policies to relearn or update the policies. The other one will be semi-supervised learning. So in case of supervised learning, we do require the input with a labeling, and the labeling has to be done manually, and it's going to be highly time consuming and very laborious activity. So to minimize this manual labeling, we can go for self-supervised learning. Then we can go for hierarchical reinforcement learning, where the high level planning and the low level controls are learned separately. So their planning is done at the high level and controls are done at the low level. So these two trainings are done separately. So let's see one by one what each one is all about. So in the batch reinforcement learning, we have the environment and our agent will explore the environment and finds what actions produce what type of rewards under which state. So at any given state, randomly, the agent will take some action and see what happens to the environment, what the state changes, and then what reward is produced, and taking this current state, current action taken, and what is the reward produced, and what is the next step. Taking this information, it does, and if the rewards are not satisfactory, then policy is updated. And with this updated policy, again, we get back to exploration and again continue our exploration. And this loop will keep learning and will update the policy, and each round the policy becomes better and better. And once we feel that we have better possible policy available or no more improvements in the policy are possible, then this policy will be used for next activities, that is for working. The other version is you can't just totally depend on the machine, so we can keep human in the loop. So here, in the place of critic, we do have human. So agent looks at the state of the environment, then takes the action, and this action will change the environment and will produce a reward. And the human is observing all these activities and will give, evaluate the situation and provide the feedback to the agent. And this feedback will help in updating the policy of the agent. And this loop keeps running, and the human gives valuable feedback to the agent so that every time the actions taken will improve and the situation becomes better and better. So that's what we call learning. So other one we can make use of is self-supervised learning. In case of self-supervised learning, we have a problem of in case of supervised learning, we have a problem of labeled data. So having sufficient number of labeled data may not be always possible. Therefore, what we can do is we can have a small set of available data and then we do some changes with this data and then each change data becomes a new data. So that way we create a new set of data and these all data are used for trading. So that's how we try to uh, make the system learn itself from a small set of data, which we call a self-learning or self-supervised learning. Then we have hierarchical reinforcement learning, wherein every action or every situation in a given system may need a different type of activity. In such case, we can have a separate policy for different activities in the system. So, at a high level, we decide which policy is better for which type of activity, and then at the low level, we apply those policies and work on uh, using those policies. We actually work with them. So these are the various types of reinforcement learning we have in our stock. So many more issues to discuss. So keep watching. Thank you.